I hope everyone can hear me. If I look to the side of my screen, I'm just admitting people from the waiting room, so we have a few stragglers I see. So yes, I think we would like to start. First of all, welcome and thank you everyone for joining. I see we have quite a nice crowd, and it's quite exciting to see we have some of people from across the world. So we have people from Brazil, we have people from Zambia, so very exciting to have everyone here today. So just a few rules. If you can, please keep your video off. It just helps with getting things to move relatively smoothly. So essentially we'll just have whoever is speaking, so either myself or Gerardo, have their video on. That just helps that things don't buffer too much. So that's just it, and then please keep your sound muted so that there's no interaction or distractions or anything like that. So yes, and then just in terms of the question and answer session, so we will have essentially today's presentation will be broken up into two sessions. So Gerardo will first speak about underground mine water reticulation, so we'll cover everything that happens underground, and then we'll have a question and answer session specifically for the underground portion. If you have a question, please pop it in the chat box. You can do that throughout, so when you hear him saying something or there's something on the slide that you have a question about, please put it in the chat box, and then what we'll do is I will then facilitate all the questions during that question and answer session that we will have halfway through for underground. And then after that question and answer session, we'll move into surface water reticulation and everything that happens in mining on surface. So yes, please then also pop your questions in the chat box for that part, and we will then do a second question and answer session. I will also, right at the end, before we do our last questions, I'll do a brief overview on ZebraTube, what we do, and specifically how we fit into the points that Gerardo touched on. The session is being recorded, so if you would like the recording, please put your email address in the chat box. I see a few people have already sent that to me, so I will then send you the recording. And you are also free to record it yourself. If you know how Zoom works, you know you can also record the session yourself, and then that will record onto your own computer. I think that is all the rules and things like that. I'm very excited about today. It's something that I think is a great opportunity for us to share information and to educate you on what happens underground, what happens on surface, and how solids moves throughout this whole process. And it is a great honor for me to present Gerardo to you as our speaker today. Gerardo and I actually go quite far back. We actually started our careers together as process engineers on the mines, and he will remember that we spent many a night shift on a Friday together sorting out all kinds of problems. So we go way back, and so it is a great honor for me to have him here today. Just a little bit about him.
Sorry.
Yes, Gerardo. Okay, so Gerardo, he holds a PhD degree in chemical engineering. And he is a registered professional engineer with the Engineering Council of South Africa. He spent 5 years working as a water treatment specialist at Sibanye-Stillwater, where he was responsible for mine water management and identifying key strategic projects focused on ensuring water security. Gerardo serves on the WISA Mine Water Managing Committee, and he recently presented at the 4th International Mining Symposium in Chemnitz in Germany. He is also a regular speaker at national symposiums by the South African Institute for Mining and Metallurgy and the International Water Association. He currently works as the head of technical environmental water solutions for the environmental consultancy OMI Solutions. And so without further ado, I will hand over to Gerardo. Let me just stop my screen share so that Gerardo can screen share.
Okay, thanks a lot, Karin. You can just check on my side. It's you switched off now, but I still can't share on my side now.
That should be fine.
Now I can. Okay. All right. Yeah. Thanks a lot for that introduction. Just want to make sure everyone's seeing my screen now. But yeah, so the purpose of the discussion today is just to give a brief introduction to mine water reticulation systems, specifically in the context of our South African mining, but it also translates well across the world. So as Karine has previously indicated, I've had quite a bit of exposure on gold and platinum mining in South Africa, and I was responsible for water management, and that's my main area of expertise. So without further ado, let's jump into the presentation. So typically in South Africa, we've got from shallow to deep mines. They can range anything from 1.4 to 2.5 kilometers, but we've also got deeper mines in excess of 3 kilometers, some of the deepest in the world actually. So the diagram on the right gives you an example of how a typical mine water reticulation system looks underground. Now, obviously, the deeper you go, you start encountering hot and humid conditions, and cooling is required to keep the working environment safe and to keep people safe from heat exhaustion, those kinds of things. So you have your water that's being cooled on surface and then sent underground. Some installations have an actual fridge plant underground as well, but that becomes a bit more complicated because even your basic maintenance is more difficult underground. So water is pumped from surface. You have your clear water dam that then gets pumped through your fridge plant, cooled to about 3 degrees, and then that's pumped to a cascade system underground where you are distributing the water as you go down level for level. So the chilled water is then used where on the mining face for equipment, for sweeping and vamping of the face after it's been blasted. And sorry, I just skipped the slide there. And as it comes back, it's at an increased temperature, and it can't be used anymore for further cooling. The chilled water is also used in bulk air coolers, which then maintains the actual ambient temperature at an acceptable level. So another source of water that adds to this reticulation system in some cases is your natural groundwater ingress. So depending on the geology surrounding your mine, you might have drilled or mined into dolomitic aquifers, and then this water will, because you are the deepest hole in the area, then all water comes in here and you have to pump that out. So in those cases, there will be separate fissure water systems and chilled water systems. So just a quick rundown of this diagram. So water gets pumped, assuming your starting point, your clear water dam, goes through the fridge plant, gets cooled, then it goes down, as I mentioned, into the cascade systems. Returning from the mining surface or the face, it gets guided through trenches and drain holes. Everything goes down to the bottom. And as you return from your mining phase, your water is at a higher temperature, as I mentioned, but you also have a lot of solids entrained. The vamping and the sweeping of the face results in very fine solids from the blasting that gets entrained in the water, and that also makes its way throughout the system. Now, the majority of these particles are less than 70 microns, so they are extremely fine, but they are from the ore itself, so it has a metal content and rock content, so it's very abrasive. And this needs to be removed from the water before it can be pumped out of a mine. Now, whether you are just advancing on or doing development work, the material you're blasting or drilling will typically be inert, But as soon as you start heading into the phase where you're mining the ore, there you can start encountering sulfide minerals, which actually has the ability to affect the chemistry of the water, and I'll talk to that in a bit more detail further on. When this water with the solids comes down to the bottom of the shaft, you typically have settlers underground, which acts as a solid liquid separation. Your clear water then goes to the gets pumped to separate dams and then gets pumped out of the shaft. This is just an illustration of the interstage pumping. Because we're talking about 1.5 to almost 3 kilometers, your pumps typically can't pump that amount of static head effectively on a single go. So you have this interstage pumping, which is another set of dams that you have to handle and maintain. Then your clear water goes back into the system that feeds your fridge plant, and this system continuously runs in a cycle and either gets topped up with fisher water or another water source. Your mud, which has your solid content and typically also a very high mineral content of which you are actually mining, will get pumped to your mud dams to surface as a parallel system to the clear water system, and then that goes to your processing plant where you can recover those minerals. So these diagrams here give you a type of illustration of how it actually looks underground for your underground settlers. There's, as mentioned, your settlers are typically your last installation at the bottom of the shaft. Your raw water comes in with the solids, either here for vertical flow settler or for horizontal flow settler that will feed in there. Now, you can have anything from 500 to 3,000 suspended solids in your water that's coming from your face, depending on how active the mining is. So all of that needs to be removed. Typically, what you're looking at is anything from 30, less than 20 to 15 suspended solids in your clear water overflow, and that's the type of quality of water that you want to pump out from underground. So obviously, you'll see here, your mixture comes in, your solids settle out at the bottom of your settler, or in this case, it's also pulled out at the bottom, and then your clear water overflows in your overflow weirs. So your settler operation is a very critical part for your water reticulation system in an underground mine, and they need to be taken care of, and your settler operators need to know what they're doing to make sure they operate functioning optimally. Then just a illustration of the type of pumps we're talking about for your clear water systems. As mentioned, they have to pump in excess of 1.5 kilometers, and the volumes can be anything from 300 to 600 cubes per hour, even higher in some cases. So it's really big machinery that's at work here, and they're expensive as well. So a lot of care needs to be taken when looking after these clear water pumps. And because of this high pressure that they have to achieve, you have to make sure you have to protect them from the solids. The very fine impeller diameter clearances that they have make them sensitive to these solids. So that's why your settler performance is such an important part in preventing damage to these pumps. Any solids that enter these pumps can damage the impellers, and this will result in reduced efficiencies. And when you're talking about pumps of a few megawatts, any efficiency losses cause horrible costs, extra costs in electricity usage. So you have to take that into account, and it's also important to monitor the efficiencies of these pumps continuously to be able to know when they're reaching the end of their effective lifespan. So as I mentioned, there's a parallel system, a clear water pumping system and a slurry pumping system. So the underflow from your settlers is gets referred to either as your mud or your slurry, which can have an SG of anything from 1.05 to 1.2. Obviously, you want your SG as high as feasibly that you can pump feasibly. because the lower the SG is, the more the water content is. So that means you're just pumping more water that should have been reporting to your clear water system. So yeah, as mentioned earlier, this is an extremely abrasive material that you're working with. So there's been a lot of optimization over the years on these mud water systems or slurry systems for them to be able to work efficiently in pumping these solids. Any operational staff will also know that your slurry pumping system is a very high maintenance portion. So it's important to do your routine maintenance, and equally important to having your standby systems available, because if you have a failure of your mud pumping system, you can't switch over, you can't pump the solids in your clear water system. So if they stop, you have to stop the entire system. So on both sides, your clear water and your slurry water system need to have duty and standby units, because you can't stop your water pumping system at any time. Then you start re-watering some of your sections, and then eventually flooding becomes a risk. So in some instances, the mud pumps are used for draining of your settlers. So they directly influence the performance of the settlers in some cases. If you can't drain the mud from your settler, your mud blanket builds up, and then eventually you start overflowing solids into your clear water, which is again exactly what you're trying to avoid. So as you can imagine, the settlers are a very integral part of this entire system. And this table just shows the main functions of your settlers, the specific part that is dependent for the function to be achieved, and then the risks that are related to not operating it effectively. So the first thing you're trying to do is you're trying to achieve clarification through the reduction in fluid rise rate. So you're basically trying to slow down the water enough so that your solids have a chance to settle out. And this is dependent on the type of design, whether it's horizontal or vertical, whether it's some of these new modifications that are done to be called high rate settlers. Now the risk you run here is if your overflow weir, which is typically a metal structure, if that starts failing and it's not completely level, then you'll start causing localized accelerated flow patterns. So this disturbs your mud bed and has the risk of entraining solids into your clear water overflow. And the other thing that is often observed at the operations is that they overload the settlers. So they would simultaneously take one or two settlers offline for maintenance and then just divert everything to the remaining settlers without actually knowing what their capacities are. And then obviously you far exceed their capacity, the rise rate is too high, and then you just can't achieve settling. Then the next function that you're also trying to do is you're trying to do pH correction and flocculation. They are very interdependent. So as mentioned, when the water comes from the mining phase, the chemistry might be effective. So, and in your mining operations, the way the chemistry is affected, because of the sulfide oxidation, you release acidity, so your pH lowers. So the water becomes corrosive. So you have to do pH correction to ensure the water is neutral at least, to be able to protect your pumps and your piping system. And then also you're trying to flocculate these very fine particles to agglomerate and become heavier so that they can actually settle out. So your flock is also pH dependent in most cases. So your pH correction and your flock dosing system has to work together. If either one of them fails, you'll start seeing solids reporting to your overflow. And then obviously what you're trying to do is you're trying to remove solids. So one of the other primary functions is the solid liquid separation. The only way you get the solids out is by pulling it off at the bottom as the mud. So if you have a problem there that it's either blocked or that you're not drawing it off fast enough, then once again, solids are going to report. So these are the important parameters that you have to keep in mind when you're looking at the operation of your underground settlers, and some of the things you must understand if you start seeing problems with the quality of the water you're pumping underground. So just talking to the actual dams that are underground, they aren't your typical constructed dams that you might imagine, as shown in the diagram here as well. Underground dams are typically underground haulage that's blocked off with a wall and connections for drawing off water, and they are the clear water dams after your settlers are directly after your settlers. So if the moment you have a failure of your settler, there's nowhere else for the water to go. If there's ice solids in there, that's going directly to your dam. So then that will cause silting up inside your dam, which reduces your capacity, but also the risk of entraining into your pumps. So if a settler is working very well, you will have suspended solids. That's the fine particles that are still in the water, will be less than 15 milligrams per liter. This water appears clear. With the naked eye, you can't really see that there are any solids in it, but there will still be less than 15 milligrams, anything from 6 to 15 milligrams per liter. But if you take into account that you are circulating 10 to 30 million liters a day, that small amount of solids can very quickly add up. So if you just look at it, you're talking about that amount of solids in the volume of water you're moving. That's 150 to 450 kilograms per day that's reporting from your settlers to your dams. Now, not all of that is going to settle out in your dam, but you can assume maybe something between 40 to 50% will settle out in your dam. And this slowly builds up over time, and therefore routine cleaning of these dams is also very important. Once your dams become too full of solids, you will start seeing the problems on the operation. Now, either if you are doing monitoring of the water quality you're pumping, you'll pick it up there. Or alternatively, if someone's standing and looking at the water being pumped, they'll see these slugs of solids coming through. Now, under normal conditions, your tank is clean and your settlers are operating well, and your suspended solids is very low. You'll see there's very little fluctuation between the actual settler overflow and the water you're pumping. But when things start going wrong, when your dam is full of solids, what will happen is they conform very well and your settler is operating perfectly, but then you see these sudden slugs of water, of solids coming through your pumps. Now, what happens here is the solids silt up inside the dam and it reaches a critical amount or volume. And then when you stop and start your pumps, you start pulling off of this sludge layer. And then you see these spikes in solids, and this can be. I've put in some conservative numbers here of 120 to 150. This can be anything as high as 300 or 400, even worse than your raw water, because it's building up over time. So it's very important to monitor the water you're pumping. You can't just rely on your settler overflow and assume everything is working fine. When you try, as mentioned before, these dams are typically a blocked off area, so cleaning them is very difficult to do. It's seen as a confined space. It's labor intensive. You have to drain the dam, and if you don't have a standby or parallel dam systems where you can clean the one and use the other one, this becomes a very dangerous and it's very important to try and do this as quickly as possible, because in some cases you actually have to stop mining, stop production to clean these dams, and that's the last thing you'll want anyone in a mine ever wants to do, because losses in production, you can't have a higher cost as that. So yeah, that's a quick run through of how the underground reticulation system works. If anyone has any questions, we'll run through that now.
Okay. Thank you, Gerardo. I think that was great. I see we have 2 questions so far. So if anyone wants any further questions, I will facilitate those questions so long. I'll see what's here in the chat box. Gerardo, Brian asks, when you get solids build up in these underground dams, is there typically any value in this material? Would it be worth it to process it further?
Okay, yeah. So the second part of my presentation will talk to that, but the short answer is yes. As mentioned before, the solids that you get back from the mining phase is what you wash down after they've been blasting, and because it's such a fine particle size, you will see that it's those solids particles are has a very high surface area. So there's a lot of exposure to oxygen or to atmosphere for the minerals to react. And as soon as they start reacting, they expose more other minerals. And if it's coming from the mining phase, this is your pyrite, and that can have interstitial gold in it as well. So the mud is actually typical in a gold mining application specifically. That mud has very high value, and because it concentrates over time, you can have a grade. You can really have significant grades in there, and your operational guys are very interested in getting that mud to the gold plant because it can have a big impact on their recoveries.
Okay, and then Alex asks, is it common to have post-filtration after the clarifiers underground? I'm assuming, Alex.
Yes, so as mentioned before, the amount of the water that's being reticulated on a mine is used for cooling. So it depends on how big your mine is, how much cooling is required underground. So the reticulation volumes quickly become very big. As I mentioned, 10 million to 30 million liters a day. So industry standard over the years has been clarifiers or settlers. There are some operations which have further filters, such as sand filters on surface, to try and bleed off these fines on a continuous basis, and just to be able to give a better quality water through your fridge plants, because your fridge plants are also very sensitive to solids. You don't want any build-up or blockages there. But having the problem with underground systems is space. It's very expensive to develop space underground, and then you've got to install this entire plant underground and all the challenges that brings for maintenance and any changes you have to do. So first prize is the settlers underground, and then if further filtration is done, I've seen it on surface. I haven't actually seen secondary filtration underground, just because of the space and the sheer volume of water that needs to be treated.
Okay, then we have one more question. I see, yes, Jaap is asking, are there any alternative option to pumping water to surface, such as spot cooling units developed by MTech?
Yeah, so there are some fridge plants that are located, the entire fridge plant is located underground. So they try and you don't have to go all the way to surface to cool and send down again. This typically happens when you start having subshafts and you're going really deep, because just moving the water, you also, all the cooling you do on surface, as you go down underground and you go into break dams and those kinds of things, you lose some of that cooling effect again. So your temperature starts increasing as you go down. So there are some cases where you have entire fridge plants underground as well. But again, this is usually a consideration you have to take into account when you're doing your mine planning from the start, because it's a big area that you have to blast or drill open, and then doing the construction, the running, maintenance. It is a bit more complicated to run this plant underground, and you are constrained for services and those kinds of things.
So I also have a question myself. You spoke about the inconsistencies that you could sometimes get and all the risks associated with settler operation, and then that causes upsets and inconsistencies, which then causes these kind of slugs of material moving to the clear water dams. How would you say that happens often? Is it a common occurrence, or would you say that's really like an anomaly? I guess you only have, you can't really say across the board, but what does it normally look like on average?
Yeah, so the typically if your settler operator knows what they're doing and you don't have many changes in your system, your settler should be a fairly consistent operation. But the problem comes in when you have severe changes in your water flow rates. A settler requires a very stable water flow rate to perform optimally. In some cases, some mines do a lot of power control, on their pumping, so they don't pump during peak times to avoid the high cost of electricity during those times. So they allow water to build up in some section where they have some buffer capacity, but then after the 3 peak hours, then they start pumping again. Then you get this massive slug of water, which is the last thing a settler wants, because now your rise rate's too high and you start draining solids. So unless that's being managed well, it can be managed so that it doesn't affect the settler, but it has the risk of upsetting the mud bed inside the settler and then just blowing solids into your dams. And then also what we've experienced on the operations is just the lack of reagents or chemicals. When you're talking about streams the size of 15 to 20 megaliters, your raw water pH is 4, and you have to raise that to about 7 or 8, then you are talking about using about 4 to 6 tons a day, which needs to be transported from surface underground to your settlers for dosing. And if you can't manage those logistics right, or if you have challenges in getting that there, then you run the risk of losing reagents or not having reagents, and then your raw water goes in, you can't raise the pH, your flocculant doesn't work, or you don't have any more flocculant, and then it's raw water in, raw water out. So I've seen some cases where operations really struggle to get a hold of it, but once you've overcome these logistic issues, and if there's pumping arrangements that have to be adjusted, it's possible to correct for these issues to prevent them from happening continuously. Are you on mute, Karim?
Apologies about that. Graham says, could Gerardo please explain why you wouldn't pump all the water and solids flow to the surface and clarify there rather than underground?
Okay, so as I mentioned, because of the water having such high solid content coming back from the mining face and it goes to the bottom of the shaft, the entire way the water travels, along the way it picks up more solids. Your pumps would just physically not last. Your impellers would be abraded if you're trying to pump even 600 or sometimes as high over 3,000 milligrams per liter. Your pumps aren't designed to handle that kind of solid content, so they would abrade. You could possibly block those pumps, and we're talking about a few million rand for one of those pumps. So it's an extremely high cost. So it has to be set. The solids have to be removed before it goes to surface. Otherwise, you just wouldn't be able to pump that kind of quality of water. Alternatively, guess if you had a really big budget for pumping, you could just put in slurry pumps and pump it all, but it's just not feasible to operate on that kind of scale because of the volumetric. If you have small volumes of water that you're reticulating, that's an option you can look at. But the moment it starts becoming big reticulation systems, I think the operating cost and the capital required for that would not make it feasible.
Okay. Yeah, so I think that's all the questions, unless there's any more. I think we can move on to the surface section.
Okay, thanks. So I'll get into that. So yeah, the second session talks more about surface water retreated, but still related to the mine water or your mining operations, as the solids that are naturally occurring as well as the solids that you might be creating through precipitation. So, okay. So mine impacted water is a term that's used a lot, but I guess the term that's used more frequently is AMD, acid mine drainage. I prefer to refer to mine impacted water because not all of your mine impacted water is acidic. I think the AMD has caused a bit of misconception in industry, because then people claim if it's not acidic, it's not impacted by the mine. So the image to the right here just tries to illustrate that. So the water coming out from the pipe is the water being pumped from underground. This water is clear. It does not appear to contain anything, but it's actually got a very high salt load. The only reason why it is reporting or appearing clear is because it has not been exposed to oxygen. It's being pumped directly from underground subsurface pumping. And the moment it starts getting into contact with air, it starts oxidizing the elements inside there, and they can start precipitating. So in the image here, you can see the clear water coming in, and then almost the immediate color change that's apparent when it turns more green. The chemical being dosed there is just a lime solution to increase the pH further, to accelerate the pH rise, and to get an action towards the target of precipitating the metals that you want out of the water. So just a quick explanation of the AMD reaction. So that's when sulfide bearing minerals comes into contact with oxygen and water. The sulfides start oxidizing to sulfates. This releases free acidity, which lowers your pH. Sulfates now in the water, and your metal, which was bonded to the sulfide, of which the most common is iron in pyrite, they both go into solution, and when they start oxidizing, they form precipitate. So what we do is that's very well, and then which this is more going unfair. This is got a crystal structure. And it bonds easily to other ferric hydroxide particles, so it forms a more dense solid particle that you can settle out. So precipitation is a very well-known treatment methodology for mining impacted water, and what this can achieve is to precipitate the metals out of solution. Now, any time where mining impacted water needs to be discharged into the environment, the metal content is one of your strictest limitations, so that you don't, because some of your microorganisms are very sensitive to metal content in the water, so you have to be sure you remove those metals from solution as solids, and then split it, remove it from the water before it can be discharged. So yeah, this just also serves to show that even though water that's coming from underground appears clear, you can't be sure that this water is safe, and it's always best to, wherever you have an unknown water source on your mining operations, analyze the water and to try and understand what is in that water, so that you know whether it can be reused somewhere else or whether it's safe for discharge. Talking towards the possible value of that sludge. Now, in the first section, we talked about the actual gold that you're mining. The superfines are now reporting as a sludge inside your dams. Where you're doing these precipitation reactions, you're precipitating the actual dissolved metals that were in solution as a solid. And just the example here of this was for a gold mine. You have relatively high concentrations of aluminium, nickel, even uranium that you need to remove from the water if you want to discharge it, because any time that you want to discharge water from a mine, you have to apply for a license to do that. And this is done obviously to protect the receiving environment, which is the responsibility of government. So government issues you with the license to be able to discharge any water, and then they specify what quality water you are allowed to discharge to make sure that you aren't poisoning or impacting the environment negatively. So where this is required, obviously these metals would have to be removed to much lower levels. For example, aluminium needs to be removed below 300. So if you're thinking that your limit is 300 milligrams per liter and what's coming in is 25,000, is a significant amount that you have to remove. But if you have the prospect of being able to selectively recover any of these metals, it might add the possibility of value recovery from these solids. Now, unfortunately, you don't, if you're at a gold mine, you only have a metallurgical system that's capable of recovering the gold. So these sludges won't have much value for the gold mine itself. But if the concentrations of these metals are high enough, it might be possible for the sludge to be collected, and then a secondary treatment facility could be constructed to recover some of these minerals. Now, as mentioned, this is just where I want to talk to the possible value of getting these materials out. Specifically on your surface water dams, how you would identify where you have a significant solid buildup. Worst case scenario is you only notice it when someone climbs on the side of the tank and sees there's almost half as much solids as water inside these dams, and this is the last situation you want to get to. So typically what some mines do is they just schedule routine cleaning every 6 months or once a year, depending on the system or the previous experience they have on the shaft. But in cases where you're doing a lot of precipitation underground, your precipitates are even more fine than the solids that you're mining, so they report to the overflow more easily. So you can have much quicker buildup of solids of either or precipitate in these dams. So you would have to clean more frequently. There are cases where you're doing it every 4 months. So it becomes a very continuous routine maintenance that you have to do. A way to try and prevent this from happening is to do inspections of the dams, either physical inspection, trying to see, but if you have big steel tanks, you can also use infrared. Where the solids build up at the bottom of the dam, they'll retain, they don't cool down or heat up as quickly, so they typically report as colder than the actual water that's moving the whole time. So if you inspect the side of the dam with infrared, you'll see a colder, darker layer at the bottom, and this would indicate the solid layer or the sludge that's built up over time. Now, as mentioned, if a dam starts becoming 50% full of mud as opposed to water, you've got a real problem, because your entire pumping system is designed around having specific volumes of storage capacity that you can put water into it between pumping phases. So if you if you have to pump a big amount of water in a small time, and your dam is supposed to be able to handle that water, and it's full of silt, you'll start spilling while you're doing your high volume pumping. So besides just the risk of getting solids entrained in your system, it also causes additional risk of either spilling or running out of capacity underground. So on surface, a water spill is an environmental issue. Underground, a spill of a dam becomes a safety issue. You can have flooding of areas, you can lose equipment, and it can very quickly become a disaster. So draining and cleaning of these dams is very important, but because these dams are normally such an integral part, and you don't have standby systems, this maintenance is avoided. But the more you avoid it, the bigger the risk becomes that you have to do a full shutdown for cleaning of the dam. So when you've identified that you've got a lot of sludge in a dam that needs to be cleaned, and it's sludge of value that you want to recover, you have a few options of this cleaning method. So instead of actually switching off the dam, draining it, and getting the mud out, something you can consider is online dredging of the tank, where you have a floating system where the pump is hanging on a floating system. You can dredge the bottom of your tank and then pump it through a solid liquid separating piece of equipment. The risk you run here is the moment you switch on that dredging pump, you start disturbing the bottom of the dam, which again then can cause entrainment of solids throughout the downstream units, which you don't want. But there are cases and technology partners who've optimized this method of online cleaning, and I've seen that it has been done successfully without having to cause downtime for the system. But once you have this actual slurry or that you're pumping out or sucking out with a honeysucker, now again you have to remove. You're dealing with the slurry. You want to get to a solid product that you can take to your processing facility. So the secondary treatment of the sludge, the options you have is either you have a settler, but the settler isn't the complete solution because it's a medium capital, it's a fairly expensive piece of equipment. It's fixed and it only concentrates the mud content up. You still have a slurry at the end as the output of your settler. It doesn't give you the full solution. Other options you have for getting those solids out is either a filter press or belt filter. This is just an example of a belt filter. But what this does is it's a very effective method of getting a dry solid and a clean liquid stream. But these are expensive pieces of equipment. They're normally fixed, labor intensive. So if you have one on site that you're using either for backfilling or something like that, by all means pump the sludge you have through that piece of equipment. It's going to give you the best possible results. But it's not an option if you're only going to use it every few months for cleaning of dams. The other option is you have these geotextile dewatering bags. The sludge that you're dredging or that you're getting out with a honeysucker after you've drained the tank, you can pump that directly through the bag. The solids get retained. It's easily handleable that you can pick up or take to your treatment facility, and the water just drains out and can be pumped. So it's a more mobile, short-term solution if it's something that's only done ever so often. Then just another example of where you can actually get value from precipitate or solids in your system, where the dam you see here is a holding dam, but there's a massive amount of ferric hydroxide that's precipitated in this dam. So if you were able to dredge this dam or mechanically collect the solids, you'd have fairly high purity ferric hydroxide, and this can be further treated to try and to the quality of different paint pigments, which has quite a bit of economical value, and depending on whether it's the mine itself or another third party that has a treatment facility for upgrading this material to a more valuable product, you have the possibility to get additional value recovery from precipitates, as well as the actual sediment, which is your raw ore, which is the ore that's just in very fine particles. So depending on the type of mine you're working at, whether it's gold, PGM, chrome ores, anthracite, each of these types of mines have their unique minerals in their water, as well as the fines entrained therein. So you really have to look at the overall picture to be able to understand where there's potential for value recovery and how the solids in the system will affect your operation. So yeah, basically I just tried to explain how solids in your mine water system will always be present, whether it's in high concentrations or low concentrations, and you have to take into consideration the various effects and risks they have in store for ensuring that your operation works effectively. And there's unique technologies available for every kind of solid liquid separation, and depending on the application, whether it's continuous or intermittent or short-term solutions, you have to consider all options for the solid liquid separation and achieving it. And I've found in almost all cases there's potential for value recovery from sediments, precipitates, if you look closely enough at how you can recover those minerals. So never just throw away sludge or solids without having a clear understanding of how they got there. Otherwise you might be shooting yourself in the foot. But yeah, thanks. That concludes the presentation. And yeah, we'll go into another question and answer session.
Okay, so I would recommend, if you guys have any questions regarding the surface solids management that Gerardo went through now, that you just drop it in the chat box. We'll speak about that now, and then after this question and answer session, I will just give a very brief overview of ZebraTube and how we then fit into each of these kind of points that Gerardo has spoken about. So, okay, let's see what we have here. Job asks, to what extent is membrane recovery processes gaining traction in the treatment of mine impacted water?
Okay, so the advancement of technology in membrane, specifically membrane treatment, has allowed it to become a more economical option that's being considered. A lot of mines, especially in South Africa, because we have such high water constraints, mines have realized the importance of having independent sources of water available to their operations, because your gold plants, your mining operations require a certain availability of potable water. And I've seen a number of mines who are investing in membrane technology to treat their mining impacted water to potable standard, so that they firstly have an independent source that's always at a very high availability for their operations. And also in some cases, if your water hasn't been that heavily impacted by the elements in the water, it can actually be cost effective, so much so that you could save money by treating your own water instead of having to buy it from the municipality. So it's becoming increasingly a better option to investigate for the mine houses.
Thank you for that. Right, Nicholas asks, in your experience, what is the typical concentration of sulfate in AMD in both Witwatersrand Basin and Mpumalanga coal fields?
So in the Witwatersrand, there's three big mine water treatment facilities: Western Basin, Central Basin, Eastern Basin. Where Western Basin, I guess, has the most concentrated impacted or mine impacted water that they're treating from historically mined out areas that were rewatered. I've seen when the water was at its worst, the sulfate concentration was in excess of, I think, I don't want to say too high, but at 3,000, 4,000. But over time, that quality has changed as well. It's gone down almost to the saturation of gypsum at the Western Basin specifically. The other basins treat more, they treat a blend of waters. So they, in those cases, they don't have those high levels of sulfates in the water. On the Mpumalanga side, on the coal fields, they have very high levels of sulfates, especially like an example, the Malahleni water treatment facility where they do the membrane treatment and gypsum precipitation. They have interstage gypsum precipitators, and there they are far in excess of the gypsum saturation of around 2,500. So they get it at a lot higher as well, where it needs to be removed.
Okay, Berger, I'm going to skip your question because it's specifically geobag related, so I'll speak to that in a second. Andrew asks, this is a difficult one as well. Andrew asks, do you have a high level or indicative cost comparison between the different methods for the removal of solids?
Short answer is no, I can't give you anything you can quote on that. But yeah, no, so between the belt filter and the filter press technology, I think those two technologies come in fairly close to each other depending on the type of design. There have been improvements on well, both those technologies, but I guess the belt filter there's been a significant amount of more improvements on the belt filter as opposed to the filter press recently. So I've seen more applications where the belt filters have been installed, and the older installations, I guess, would be the filter press. Your settler is definitely a cheaper capital option than either one of those two, but it's again, still gives you a slurry. Both the other technologies gives you a solid final dried product. And then the geotextile bags, obviously there's no capital requirement there. It's seen more as a operational, as a expendable product that you use as required. So it makes it a bit more flexible, and you don't have to have this big capital up front, and you can implement it fairly quickly. But yeah, sorry, I don't know. I can't give you a more rands and cents answer than that.
Well, that is a difficult one to answer just like that. Okay, and then Mira asks, what happens to the drained water once the sediments have been recovered?
So that's a very site-specific question, I would say. So if it's in a mine service water system that you're cleaning a tank and taking out solids, you would just drain the water to a sump and put it back into the entire reticulation system. If it's an application where you've precipitated solids from from a raw water, and then you typically would throw the water just back into the system wherever you got it out of. Especially if it's a application where you're just doing a routine cleaning of the system. However, if it's a more continuous installation where you're actively dewatering solids, you might look at the option of taking that water and upscaling it with either additional filtration or membrane filtration to get a more usable water out of it as a product, like potable or at least service water or agriculture water quality.
Yeah, I can also maybe add to that, but specifically more on the geotextile bag part. If you are using geotextile tubes to clean dams, surface dams specifically, you would typically position them either such that your filtrate would run directly back into the dam, or you would have a sump of some sorts on the sloped end of your geotextile bags, which then allows you to use a sump pump to recover that filtrate. So yeah, most of the time, Gerardo, I agree with you that you would typically, on most applications, return that back into the system. Okay, so what I think I'll do is, Gerardo, if you just stop screen sharing quickly, then I can quickly do my bit. It's slightly over time, so I hope everyone is being is patient enough. Let's get this going. Okay, so I'm going to start by just showing you guys a video. The video is an animated video that just gives you a very good overview of how the two different, basically the main overarching ZebraTube product options works. And then I will just touch on a few points that Gerardo mentioned, how the ZebraTube product integrates into the mine water reticulation system.
Are you faced with sediment buildup in dams or liquid waste streams that are difficult to dispose of? ZebraTube's engineered geotextile bags offer fast, flexible, efficient, and cost-effective dewatering solutions. Applications can include dewatering of food and beverage and industrial waste, to dredging and containment of sewage, silt, and natural resources. Small-scale projects can be dewatered using our unique, easily handled 1 to 5 ton bags. Larger projects make use of our tubular bags. In certain applications, flocculant can be added to agglomerate solids to enable efficient settling. Once dewatered, the contained material is dry enough to be easily disposed of or reused. In addition, the filtrate can be collected for reuse. Contact ZebraTube now for your custom-made solution.
So Gerardo did mention quite a few points where the ZebraTube product does come into play, and one of the first things that he spoke around is obviously underground. And yeah, I actually haven't heard those numbers before, Gerardo, so that was interesting to me how you said even for a a perfectly operating settler, you have between 150 to 450 kilograms per day, at best, being sent to your clear water dams. So that is why you do ultimately get solids and silt buildup even in your underground clear water dams. And underground dam cleaning is definitely something that has a lot of challenges due to the confined space that you have available. And so we've done quite a few of these underground dam cleaning projects where you would use the geotextile bags underground during this dam cleaning operation, pumping the silt from underground clear water dams into our small scale bag, which is what you saw on the video, which is basically looks like a bulk bag format, what you see on the screen as well. And we do them either open top like that, or we do them with a funnel top, which obviously prevents spillage if you need that. And they come in a 1 ton or 5 ton format, and you can essentially move that bag so easily, which is something that we've seen works very well in a confined and underground space, in order to then move that material to surface. So on the few underground applications that we have worked with underground contractors in cleaning dams, they would clean the dam, the silt would go into the dewatering bag, and once the material is completely dewatered and the filtrate is drained out, that bag would then be moved and it would go to surface with all haulage, which is obviously important. As Gerardo mentioned in one of the questions, you do a lot of the times find that this underground mud buildup has a very high grade, especially in gold, and it's quite important to make sure that you can actually recover that material. Then we also do a lot of geotextile bags for the surface dam cleaning projects. As you can see, the picture on the screen there just shows you the bags essentially lined up and stacked like that. We've also worked with quite a few people that has specifically looked at dredging and dredging line dams, for example, and then pumping that into these dewatering tubes. And after a fair amount of you get this solids relatively dry and can then easily be moved in order to be reprocessed for whatever value might be in that material. The other thing that's quite important about the geotextile bags as well is that, as Gerardo also mentioned, if you're doing a non-permanent kind of dewatering, such as a dredging or a surface dam cleaning operation, you wouldn't necessarily want to fork out the capital to build a belt press or a belt filter or a filter press. The bags are a quick, easy, cost-effective way to dewater and contain the solids that is in the surface dam. They're also stackable, which means that you can very effectively adjust to production requirements. You can also change your size very easily. So it is something that is just very adjustable according to whatever production or dredging requirements you are working on within a certain week. So whereas with capital equipment, you might find that you have a certain production requirement, and that's certain you within those confines. Whereas the dewatering tubes enables you to very effectively adjust according to your production requirements. Then moving on to the process plant and the surface applications, they're quite wide-ranging, but I just specifically quickly wanted to touch on 2 examples of where we've actually used our geotextile tubes and bags on process plant surface applications for recovery of valuable materials. One example is Magnetite Recovery that we've done at a coal processing plant, which is the picture you see on the top left here. And that's also a project that we had spillage and basically solids overflow of magnetite on the sumps of a coal processing plant, and that was pumped out into the dewatering tubes. And interestingly enough, because magnetite is such a low SG, such a high SG, excuse me, it settles so well inside the tube, and you can get very, very good moisture contents after very short drainage periods. So for this specific project, after only 2 weeks of drainage time, standing time after the tube had been full, we had around a 10% moisture content in the dewatered material, which is very dry and can then very easily be moved and reused and reprocessed in the plant. Another example that I know Gerardo is also familiar with, because it is a bold application, we commonly utilize the square or smaller scale format dewatering tube in the carbon fines recovery on a gold plant. Carbon fines are typically contain quite a lot of gold still that needs to be recovered, and this is another good example of a very cost-effective way to recover the water and then contain the carbon fines. And because of the format of the bag, it's so easy to then come with a forklift and just move it as is to wherever you would like to process it in the process plant. So that is just a very, very quick overview of ZebraTube and where we fit in. I think I will now take some questions. If there's any further questions on the ZebraTube specifically, just want to open my chat box. Okay. So I know Berger asked earlier, what size geobags would you recommend to pump the sludge into? So that's a very difficult question to answer because it's so application specific. And the nice thing about ZebraTube as well is we're very flexible in terms of the sizing that we do. So we do custom design based on whatever your requirements is. So in order to get a sizing for whichever sludge application you have, I would typically say contact ZebraTube and we will do a sizing calculation according to your requirements. And just to give you an example of where we've done some custom sizing, also in an underground application, we've done bags that fit exactly into the hoppers for the underground earth moving equipment so that people can pump and move it directly and then go to all the wedge. So that was another example of where, according to the context, we would then size and design according to whatever the requirements are. I hope that answers your question, Birgit. Then we have Parker asking, what is the lifespan of the bags? So essentially, yeah, it's a difficult question to answer, but essentially it's, I would say the big thing is UV considerations. Normal geotextile bag, the way we make them as a standard, 3 to 5 years under UV exposure. But we have done projects where we needed to have increased UV exposure, and then we would add a special, normally non-woven covering to the bag that then increases your UV exposure lifespan to over 10 years. So UV is probably the only main thing that you should be concerned about if you would like the bag to become a permanent containment for your solids. Other than that, it's very durable because it is made from polypropylene, so it is very durable. Right. There's another one. Then Alex asks, are there limitations to the pH of the sludges that can be filtered with your bags? There actually isn't. It's just important that you tell us that it's going to be a low pH or a very high pH application, because what we need to do is just, obviously the woven geotextile is made from polypropylene, so it's very durable. The main thing that we need to change is the thread that we stitch with. So if there is a low pH application, we change the thread, and then your bag is very durable to the low pH conditions. So it is just important to just note, if you are inquiring with ZebraTube regarding low pHs, that we don't then make a standard bag, so that we make sure that the actual thread that we stitch with is for lower pH applications. Okay, then there's another question asking, are these bags and tubes reusable or single use? Also, is it woven or non-woven? So yes, it is a woven geotextile that we use for the ZebraTube. Sometimes, as I mentioned, we would add a non-woven covering, but that's only if we have UV exposure issues. So it is, as a standard, it's a woven polypropylene geotextile. And then in terms of the bags being reusable, generally no. And the reason I say that is we are very dependent on the lining of the textile in order for you to get really good solids retention and filtration. So what would happen is you would pump your slurry in, and as you start pumping, and it's also why a lot of people would have heard me say, okay, when you start, you have to pump really slowly so that you can start getting that little bit of lining and a little bit of formation of a filter cake on the inside of the geotextile. And so that formation of that filter cake and the lining of the in between your woven pores is so important for you to get good filtration efficiency and good solids retention, that if you then try to reuse, for example, the square bag, which is the only one you really can try and reuse because you can then remove the solids and try to wash it out, you wouldn't really get the same efficiency when you go back and you try to reuse it. There has been like the odd one or two customers that would try to reuse it maybe once or twice, then you really do lose that efficiency. In terms of the tubular concept, the tubular bag, so the tubular bag, you obviously, as you would have seen in the video, you pump it in, and then once it's dry, you break open the bag in order to come in with some kind of earth moving equipment to move the bag. So once you've done that, obviously you can't reuse it. So the short answer actually is it's not really reusable. Nigel asks, have the bags been used in small to medium domestic effluent treatment plants for solids removal and drying prior to stabilization, reuse, or transfer to landfill? Yes, so we've done, I would say, 4 or 5 different small-scale effluent treatment plants where we would sell typically the square concept, either a 1-ton or a 5-ton bag that then is used in that application. And it's very important that you mention the landfill concept, because as you would probably know, landfill legislation very recently changed, and you need quite a good moisture content. It needs to be relatively dry in order for material to go to landfill. And so yes, we have done that, and ongoing we supply these square bags on a monthly basis to these kind of effluent plants. We've also done it now in the past 3 or 4 months. We sell quite often the square bag concept to food and beverage because they are also constrained by landfill applications. So if they produce some kind of food and beverage waste, that's another example of where they would need to dewater it before it goes to landfill. So that's another example of where, yes, they do get used often in that kind of application. Okay, Alex asked, what is the solids micron rating that you can down to, or is there a range? This is also very application dependent, specifically because we rely on the formation of that filter cake in order to aid filtration. So, but what I can tell you is that we can go down to 10 micron particle size in terms of solids retention. We just typically say, it's just a kind of a rule of thumb, if you have more than 30% in minus 10 micron, then you typically need to use a flocculant or some kind of a filter aid in order to aid in that filtration. But yes, we can go as small as minus 10 micron, and then obviously above that. Okay. Nigel asks, are the bags PE? Can they go to reuse applications, pyrolysis, incineration? It's polyprop. I'm assuming yes, you can. I mean, it's still a plastic application, so there could potentially be a reuse application for the actual material of the bags. Definitely. Yeah. So far, no other questions. Yeah, if there's no further questions, then I think we will sign off. I hope everyone enjoyed it. I hope it was informative. I'd like to say very much thank you to Gerardo. You are so knowledgeable. You know so much about everything around mine water. And what I thought was very good is the being able to really see it from all the way from underground up to surface and how everything is connected. Because I think that especially like if you're a process engineer, you work on surface, you don't always understand that necessarily the impact that underground applications have on what's happening on surface and vice versa. So thank you very much for that. And I hope everyone enjoyed it. And just to let you know, we will be doing another webinar in the series that will most probably focus on wastewater, so municipal domestic wastewater. So keep your eyes out for that. And yeah, I will send everyone who sent me their email addresses in the chat box. I will send you the recording, and you can also have a look at it. We were live on Facebook, so it should still be on our Facebook page. Thank you, everyone.
Thanks everyone for being here. Hope everyone found it informative. If you have any questions or want to discuss anything, feel free to reach out to us, and we can hopefully assist.
Great, thank you, everyone.